So as we move on, we're going to be looking at statistical distributions, and we'll be formalizing some of the probability work that we've done before. Let's start off with some definitions and clarifying exactly what things are. A variable in statistics is going to be any characteristic or a number or a quantity that we can measure, anything that can be counted. So a variable in algebra is very different. That usually takes the form of an unknown value. We're talking about things like the number of times you're late to school within a week. This can be counted. The number of siblings that a person has. This, once again, can be counted. Now, a variable can take any of a range of specific values, and we can usually outline what these values are going to be, or at least give a range that these values can be within. The number of times that you're late to school in a week, it has to take a value in between 0 and 5. You can't be late less than 0 times, and you can't be late any more than 5 times. Being late to school 8 times in 5 days would be strange. Is the variable discrete or is it continuous? A discrete variable can only take specific numerical values. It's either 1 or it's 2 or it's 3, etc. Continuous, on the other hand, that could take any numerical decimal value within the range. So 1.2 would be acceptable, 1.27, 1.2759, as many decimal places as you would like. We're not going to look at continuous variables at the moment. We're just focusing on the discrete variables. And the concept of random when referring to a variable is if the outcome is not yet known. If we have to wait until the experiment is carried out to know the outcome. If we try to make a probability distribution, a statistical distribution of the weather yesterday, that wouldn't be random. That event has already occurred. That event is fixed. There is no randomness to that event. If we were making a statistical distribution about the likelihood of the weather over the next 6 days, well, yeah, there is some randomness to that. Discrete random variables are what we're going to be looking at. Sometimes we'll just look at random variables which don't have numerical outcomes, but mostly we're going to focus in on the discrete random variables. Discrete because it can only take numerical values, random because the outcome is not already known, and a variable because it's a characteristic or a quantity that we're measuring. And you'll see how this plays through as we go through. We already know that all of the outcomes of an experiment are called its sample space, all of the possible outcomes to that particular experiment. So we can refer to the range of values that a random variable can take as the sample space. Let's have a look at this random variable. It's not discrete because the outcomes are not numerical. The outcomes are colors on a spinner. But here's all the possible colors we can get on the spinner: red, green, blue, and orange. Once I've assigned probabilities to each of these outcomes, we have the probability distribution of this random variable. Every possible outcome and the probabilities associated with it. The notation here is going to take some getting used to. It reads the probability that x equals x, which just sounds very trivial, but we have a difference between the capital X and the lowercase x. The capital X in this case represents the actual random variable, the experiment that was carried out, while the lowercase is going to represent a specific outcome to that experiment. So we would read this statement as the probability that the outcome of the random variable x equals a specific outcome x. In this particular case, we may well have the probability that the outcome of the spinner when spun, or when we ask a person what their favorite color is. So the the probability that the outcome of us asking a person their favorite color is orange. Now that whole sentence can be summarized in this statement. The probability that X equals orange. The probability that the result of us asking the question leads to an answer which is orange. And the answer to that is 0.2. The probability that X equals orange is 0.2. Similarly, the probability that the outcome of the color that a student picks when asked their favorite color is blue, that long sentence can be summarized in this statement, the probability that X equals blue. The answer, 0.1. The probability that the outcome of the color that a student picks when asked their favorite color is green, summarized as P, X equals green. Answer being 0.4. So this is shorthand for actually quite a lengthy probability statement. So when you do read probability that X equals X, you know that we're creating shorthand for a much longer statement. Okay, so let's have a look at a couple of ways for us to summarize outcomes or the sample space and its associated probabilities. We could describe those outcomes using a function. So here I have a piecewise function. What that means is that there's two different rules, or there are multiple rules. In this case, there's two. We'll use the top one for the values shown in the top row. So that's X equals 1, 2, 3, and 4. And we'll use the bottom one, which is actually just 0, for all of the other values. We write the phrase otherwise for all of the other values. So we can go ahead and find out probabilities by substituting them into this function. So when X equals 1, we'll have 0.1 multiplied by 1, 0.1. When X equals 2, we'll have 0.1 multiplied by 2, 0.2. When X equals 3, we'll get 0.3. When X equals 4, we'll get 0.4. This was quite a straightforward function, and the choice of the X values allowed for it to work well. We won't always get something as straightforward or easy as this, and we'll look at some examples of that later on. We can show all of those outcomes that we just mentioned in a table, which is probably the more familiar and maybe even the easier to read out of the two of them. Now, there are advantages to using a function and advantages to using the table. The advantage of using the function is that if we actually had a very long table, let's say there were 20 different outcomes and lots of them were similar, or lots of them had a function that could describe them, it's easier to show as a rule. It's easier to show as an expression, and it's just quicker for us to write that down. The advantage of the table, assuming that it's not trying to cater for a huge amount of outcomes, is that we can very quickly see the corresponding probabilities to each of the outcomes. And it's a little bit easier to work with for further work that we do around a discrete random variable. Okay, so let's just go through an example here. The random variable X represents the number of heads when 3 coins are tossed. So we're tossing 3 coins. How many heads do we get? First, let's start with the sample space. What are all the possible outcomes that we might have? Now, we'll try and go systematically. I can get 3 heads, or I can get heads, tails. These are the two options that start with 2 heads, and I've just alternated the last coin for heads and tails. Let's have a look at the options that start with a head and then a tails. So heads, tails, heads, tails, tails. Now these are all of the options where the first coin was a heads. So I'll do a similar thought process for where the first coin is actually a tails. And we have 8 possible outcomes, 8 equally likely outcomes for tossing 3 coins together. You can't really get a two-way table, a sample space diagram as you're used to, if there's more than 2 events happening in succession. So we had to be systematic in writing these out. What does that look like as a table? Only one of these outcomes had no heads, 1 out of 8. 3 of these outcomes had just 1 heads. 3 of these outcomes had 2 heads. Only 1 of these outcomes had 3 heads. So that's how we generate these probabilities. 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. So, the original sample space, a probability distribution, a table for our sample space and probabilities. As I said before, if we have like repeated probabilities, we could summarize them in this piecewise function. So the probability of a specific outcome equals 1 over 8 for the outcomes 0 and 3, or it equals 3 over 8 for the outcomes 1 and 2, and it equals 0 for everything else. So that's how I'm reading through that function there. And lastly, we could actually graph this. So this is what the distribution looks like as a graph. The number of heads achieved when 3 coins are tossed. 4 different ways to represent the outcomes and their probabilities. Okay, so you would need to be fluent and comfortable with each of these different depictions. The 2 most common ones that you're going to be using are the table, the probability distribution, and the probability mass function. Okay, let's have a look at what happens when we have cumulative probabilities. Cumulative probabilities are when we have a range of outcomes that we want to combine together. It's similar to an event. It's a combination of the individual outcomes to an experiment. The probability that x is greater than 3. I think the first thing here is actually to write this as the probability that x is greater than or equal to 4. Let's actually use the values that we're interested in rather than the values we're not interested in. So x is greater than or equal to 4, and we can see here that that is going to be 0.6. On to the next one. The way I'd read this is the probability that x is in between 2 and 4. 2 is included, 4 is not included. It may well just be easier to write this as the probability that x is in between 2 and 3, where both of them are included. So once again, we're trying to write this statement in terms of the values that are included. 4 was not included, 3 is going to be included. We want x to be smaller than 4, but not to include 4, so that means 3 is the largest number that is included. Just taking a couple of seconds to think through these inequality statements will usually set you up to respond to this question correctly. Okay, and that leads to an answer of 0.4. This third one, students usually see this and aren't sure how to proceed. But if we just hone in on what we have in the brackets, we just have an inequality that can be rearranged and we can set x to the subject. So let's go ahead and do that first before we think about any probabilities. I'm going to try and isolate the x. So I'm going to subtract 1 from each side and then divide each side by 2. And that gives us the probability that x is greater than or equal to 2.5. Looking at the probability distribution, there is no 2.5. It's either 2 or it's 3. So in saying it's greater than or equal to 2.5, that's exactly the same as saying it's greater than or equal to 3. There is no 2.7, 2.8, 2.9. The next available number to refer to is 3. The probability that x is greater than or equal to 3 is going to equal 0.9. Okay, so that's cumulative probabilities. We just want to look at one more type of question that's very popular when you're working with discrete random variables. So here we have a probability function, and if you notice, the probability function itself is in terms of k and x. We expected x. That's a variable that we can substitute in. We have 4 different values that x can take, -1, 0, 1, and 2. So we expected an x that we would substitute into. But what are we doing with the k? This type of question is going to ask you to find the value of k. Luckily enough, in this one, it's a show that question, so we know the answer that we're aiming for. With all show that questions, we cannot start with the answer and work backwards. We need to ignore that and just make sure that we end up with that same value from our own working out. we need to just go ahead with the techniques that we already know how to use. We know that we can substitute each of these x values in, and it should give me an expression for a probability. The key thing here, though, is that just as we've seen so many times with probability, that the probabilities are exhaustive. This means that all of the probabilities will add up to 1. And this makes sense since this was the sample space. This was all of the possible values, all of the possible outcomes that the experiment can yield. If all of the outcomes are catered for, then all of the probabilities are catered for, and we know that probabilities will sum to 1, as in 100%. So we're just going to go ahead and we're going to do our substitution, and we're going to get probabilities in terms of k, but we're going to use that fact to help us find k. Okay, so the probability that x equals -1 is going to equal k, and in my brackets I've got 1 minus -1, close the bracket and square it. Should be able to do this bit on our heads. That's going to be 2. So 2 squared is 4. That gives us 4k. The probability that x equals 0, we're going to substitute in 0. That gives us k times 1 squared, which is just going to be k. The probability that x equals 1. 1 minus 1 is actually going to be 0. I don't even need to process anything any further. The probability here is 0. It's impossible to get a result of 1. Just because it was in the table doesn't mean the probability won't be 0. Probability that x equals 2. Substitute in the 2, and we've got k times 1 minus 2, all squared. So that's -1 squared. So from there we get k. All of these can be written in the probability distribution. And from there I'll get 4k plus k equals 1. Sum it together, make k the subject, and we see that k does indeed equal 1/6. So this is a very popular type of question, just look out for it. The fact that the probabilities add up to 1. You won't be told in the question, this is just expected knowledge. The examiner is going to expect that you know this. Now, just be on the lookout for one specific type of discrete random variable, or one particular type of statistical distribution. This is called a uniform distribution, and you've actually come across quite a few of these up to now already. Uniform distribution is any distribution where each of the outcomes has the same probability of happening. Flipping a fair coin is a uniform distribution. Both the heads and the tails are equally likely to happen. Those are the only two outcomes we can have, and they both have the same probability of happening. Throwing a dice, that would be a discrete uniform distribution because we have numerical outcomes. The coin didn't have numerical outcomes if we refer to it as heads and tails, but a dice, the score that we get, numerical outcomes, this is now a discrete uniform distribution. Each outcome has the same probability of occurring. This is quite easily seen as a graph. In the table, every value for the probability would be the same. You are sometimes asked to recognize and to refer to a discrete uniform distribution. You notice that the probabilities are uniform across the distribution. So, we've looked at discrete random variables, we've looked at the terminology, we looked at 4 different ways for you to show the probabilities that might arise from a discrete random variable. We've looked at cumulative probabilities and how you rewrite them to use inclusive numerical values and how you read those values from the table. And lastly, we've looked at this specific type of question when we're asked to find the unknown value of k. Okay, I'll leave you to get some practice in,